Okay, so our final talk of this session is going to be given by Andrew Young, who's going to be talking about quantum dots and quantum technology, and he's from our group at the University of Bristol.
Thank you. Welcome to the final talk of the day. So if you weren't convinced by the previous 3 talks on this topic, I've got another one. And it's about how quantum dots are useful for quantum technologies, whilst also discussing some of the limitations. I've done this as more of a sort of overview-based talk with a few sprinklings of some of the results we've got from our research in Bristol. So if you've got any more technical questions that you want to ask, you can of course ask me or any of the names on this list. Most of them are in the room today. So when I was thought about preparing this talk, I was thinking, well, it's an overview talk at a technology conference. I need some fancy images, some nice pictures. And I'm not very good at drawing fancy images and pictures, so I thought, I'll do a Google image search. I did a Google image search for quantum dot technologies, and I was slightly taken aback by some of the images I found. So these rather unfortunately shaped containers contain colloidal quantum dots. Now, the reason that I put this up here is not just because it's stupid and looks funny, it's because it's to emphasize that quantum dots really aren't this kind of future tech that's still stuck in the lab. There is actually technologies out there that are already using quantum dots. So one example, this is from a while ago, but it's from where these colloidal quantum dots have been injected into this rat in order to fluorescently tag cancer cells. And more recently, the biggest noise has been coming out of Samsung, who've been putting these colloidal quantum dots in their production, into their latest display technology. If you like, it's a quantum leap in television. So the reasons behind that, you can find a helpful cartoon on the Samsung website, in fact. And this fella over here is a green quantum dot, and it's saying, we may be nano-sized, but we're pretty powerful when it comes to color. And the small blue quantum dot in the middle is very excited by this, and is saying, yeah, quantum dot color power. Well, these colloidal quantum dots are not the ones I want to talk about today. What I want to talk about are these grey blobs in this picture here. So these are just like the quantum dots we've heard about in the previous 3 talks. They're indium gallium arsenide quantum dots, and they're formed into these little islands by a grown gallium arsenide strain, forms them into these little islands. We cap them off with some more gallium arsenide, and then because of the difference in the band gap and the size of the structures, only a few tens of nanometers, we get quantum confinement. And that leads to a discrete set of energy states, where I've joined the first 2 here. So what we can do is take an electron from our valence band, we can put it in the conduction band, leave behind a hole, that forms an exciton, and then at some point later that's going to recombine and give me a photon. And it's that mechanism that's really central to how quantum dots can be useful for quantum technologies. Particularly in these 3-5 semiconductor systems, where the photonics engineering, as we've seen in the various talks previously, is already fairly advanced. So we can embed these quantum dots into really high quality photonic structures. And that's absolutely key if we want to be able to input and collect single photons from these devices with any sort of efficiency, and we want to scale things to larger photon numbers. So in terms of where quantum dots sit in quantum technologies, I've got this slide here with some interesting examples. You might recognize them from the previous talks because they're very good examples. So the first one here we've just seen is where you're using the quantum dots as a single photon source, a highly efficient source of indistinguishable photons, and they're using it to do boson sampling. I don't need to tell you any more about that. This one down here is from Mete's group, where they're using quantum dots to form a sort of nodes, if you like, in a quantum network to share and distribute entanglement over potentially large distances, and that's kind of like the prototype of the quantum internet, if you like. And the final example here is where the internal state of a quantum dot is being used to switch single photons between 2 orthogonal states. And what you can do with that is you can take that and replace the beam splitters in your linear optics with one of these sort of switches. And if you do that, you kind of get entanglement as well for free at the same time, which really helps you scale these systems to larger photon numbers. So that's where quantum dots sit, I think, in the quantum technology platform. It's really combining quantum dots with single photons. We've already seen our first quantum dot-based spinouts. The 2 that I have on this slide, conveniently the 2 that are at the back and are sponsoring this event. We've got Sparrow Quantum and Quandela, and they're both making quantum dot-based single photon sources. Sparrow using photonic crystal waveguides. We've already had an excellent talk from Quandela, so showing how their micropillar architecture. And both of these sources are excellent, and you should talk to the people at the back and both go out and buy both of them. But there's still some limitations even with these best sources in the world, and it's really that the usable efficiency of the photons that you get out is somewhere in the region of 10 to 50%, depending on your use case, whether or not you want your photons to be indistinguishable or not. And if you want them to be indistinguishable, you tend to be sitting at the lower end of this efficiency spectrum. So that brings me on to what I think is one of the first challenges for quantum dots as a quantum technology is the efficiency. The efficiency that you can input and collect single photons from these devices. So the current best devices, and we've already seen reports of them so far at this conference, have fantastic values for indistinguishability and brightness, and the intrinsic device efficiency sits somewhere in the 65 to 75% region. In fact, the Quandela talk now, I need to change that to 80%. But then by the time you add your external optics and all the collection on top of that, you can reduce it by a factor of 2 up to around a factor of 10. So where's all the light going? So I'm first going to look at the intrinsic efficiency of these photonic devices, and I'm going to use the micropillar as an example because they are the ones that already have the records for brightness and indistinguishability. So you make your micropillar, as we've seen in the previous slides, by etching these cylinders through your quantum dot wafer, where you've grown mirrors either side of the wavelength scale there where your quantum dots sit, and here's like a zoom of your cavity in this cartoon, and I don't know if you can make it out, the red blob in the middle here is a quantum dot, and that's going to give me single photons. And those single photons basically have 2 channels where they can decay. They can completely ignore this cavity and go straight out the side here, which we don't want to happen. What we want is the single photons to couple into this cavity mode and begin to circulate. And the extent to which our single photons couple into the cavity mode will be parameterized by this beta factor here. Now, once the photons are inside the cavity mode and bouncing around, what I then want to be able to do is to steer them reliably out into a single mode towards my detectors. So in the micropillar example here, what I want is for them to come out through this top mirror and make their way all the way to my detectors. Unfortunately, there still are some other loss mechanisms. Even when the light's bouncing around in the cavity, it can scatter out of the sides, or it can go through the bottom mirror. We can limit the bottom losses just by basically having more mirror pairs on the bottom than the top, so the reflectivity down here is higher than the reflectivity up here. And the extent to which light that's bouncing around in the cavity then comes out the top is parameterized by this e to top value here. Now the goal to get high intrinsic efficiency is obviously to maximize both of these values at the same time. So in the sources you've seen so far today, this beta factor is really high, it's really well optimized, but what's letting the sources down currently and limiting them is the e to top, the rate that those photons get extracted from the cavity and out through the top mirror. So why is that? So we've got our SEM images of some pillars here and my badly drawn cartoon. So light's bouncing around inside my cavity, and as it does that, it interacts with the sidewalls of this micropillar. And despite what this image suggests, the sidewalls are slightly roughened, not to this extent. This is an exaggeration, of course. What that does is, as the light's bouncing around in the cavity, it sees these imperfections in the sidewalls, and it can scatter out the side. And this is limited by the way the pillars are etched, and really to improve on that, you need to etch really straight edges down your micropillar. And it's quite a hard thing to improve it, certainly in the short term anyway. So one thing you could do is potentially increase the rate that light comes out through the top mirror, and you do that basically by reducing the reflectivity of this mirror. But if you do that, then you're lowering the whole quality factor of the entire micropillar cavity, which has a knock-on effect that it reduces the rate the photons went into the cavity mode in the first place. So there's a balancing act that you need to perform, certainly in order to optimize structures based on current fabrication technology. And it turns out like a decent compromise is a low quality factor micropillar. So the one we have in Bristol has 18.5 bottom mirror pairs, 5 mirror pairs on the top, it's 2 microns in diameter, and it only has a Q factor of around 300. And the reason the Q factor is so low is because the reflectivity of this mirror has been reduced such that the escape rate is very fast and it dominates over all the sort of other lossy channels. The theoretical beta factor in this structure can be up to 0.85 for a quantum dot that's bang on resonance for this cavity mode. And with a few further optimizations and fiddling around, we've simulated similar structures where you've got the product of beta and e to top to be around 0.92, so that is an intrinsic efficiency of 0.92. For this specific pillar, we measured the values and we got an e to top greater than 0.9 and the beta greater than 0.6. And the reason these are lower bounds is because our measurement has background. And that background is due to mode mismatch between the micropillar mode and the external collection optic. So that brings me on to the second piece of the efficiency puzzle, which is the collection efficiency. I need to, beyond the intrinsic efficiency of the device, I need to be able to get the photon out into my detectors very efficiently. So one solution is just don't collect the light at all, which sounds very simple, but it's actually going to be complicated because it requires you to directly integrate everything onto one wafer. So this example here I've lifted from the Sheffield website. So they've got photonic crystal waveguides with quantum dots in them. They're directly linked into a linear optical circuit, in this case a 50-50 directional coupler, and the superconducting detectors are also integrated onto the architecture. So that solves one way to solve the collection efficiency problem is do everything on chip and the light never has to leave. But there are certain instances where you might like to go off chip. Mete gave a very good example in his talk, which is what about if you want to communicate quantum information over larger distances and you want to build a quantum communication network. So there perhaps you might want to do some off-chip communication, so maybe fiber integration is better. But you can't just go to the Thor Labs catalogue and buy an optical fiber and glue it to the top of your photonic structure and hope that it's going to work. The refractive index contrast alone between gallium arsenide and most glass fibers makes that really difficult before you even take into account numerical apertures and mode matching and things like that. So one of the many approaches that we've been pursuing in Bristol is really co-designing the photonic structure and the output of the device. So this example here, we've got gallium arsenide half pillar in this instance, and we complete the cavity by having a fiber that's got the mirror coated onto the fiber. So this is still very much in its early stages, this work. I don't have anything quantitative to say about it at this stage, but this is the sort of things that we're thinking about in terms of really increasing the overall efficiency of these quantum dot-based technologies. So I've talked a lot about single photon sources in that section, and certainly they're a very important component to a quantum photonic network. But even with the perfect single photon sources, quantum photonics has some pretty scary scaling problems. So quantum dots, again, as we've seen in the other talks, can actually be come to the rescue again. So they can be used as switches or indeed sources to generate entanglement much more efficiently than you can do with just beam splitters on their own. So how does that work? So we now have our quantum dot energy level structure again, and we place a electron spin in the conduction band. And then what happens is we get some interesting optical selection rules depending on the state of that electron spin and also external fields and things like that. But I'm going to greatly simplify the picture for this animation here. So if my electron spin is off, any photons that come in and interact with my quantum dot are going to end up in this top propagating mode here, for example. Now if I flip my spin to down, my photons are going to switch to this orthogonal bottom propagation mode. And that forms the basis of a spin photon switch. And of course, electron spins are quantum objects, so they can take up superposition states. This is how I denote the superposition. And any photons that interact with that are also going to end up in a superposition of the two available photonic modes. And on top of that, they're going to end up entangled with each other. And then you can build up multi-photon entanglement by essentially just repeating that process over and over again. And we've seen that that's got many applications in the previous talks: quantum memories, repeaters, 2-qubit gates, cluster states. It's very many applications. So in Bristol we have our own spin photon switch. So we use the same micropillar I showed you earlier on in this talk, and we've got our quantum dot in there, and it's sat in the spin-up state. And what we do is we input vertically polarized photons. If they interact with the system while the quantum dot's in the spin-up state, well, nothing happens to them and they stay vertical. But if we have the spin in the down state, our input photons that were vertical are going to flip and switch to be horizontally polarized. And this is what the data for that looks like. So this is a rather complicated looking two-dimensional histogram. It's actually not that hard to understand. So the y-axis here denotes how many of my photons came back vertically polarized, and the x-axis is how many came back horizontally polarized. And this color map is a sort of histogram, and you can see up here we've got a peak in the distribution where we've got lots of vertically polarized photons and not very many horizontally polarized photons. So that represents times when our electron spin in that quantum dot was in the spot state. But also down here there's a secondary peak in this distribution, and that's in the region where the horizontal counts are higher and the vertical counts are lower. And that represents regions where our electron spin's in the down state. And from this measurement we can calculate a switching fidelity of around 0.7, which doesn't sound that impressive after all the previous talks talking about 99% fidelity. But actually that's significantly higher than anyone's ever reported in the past. And importantly, it really is not intrinsically limited by the device itself, it's limited by the collection efficiency. So again, the mode match between our micropillar mode and our external optics. And if you're really staring at this graph and paying attention, which you're probably not, you might notice that this peak in the distribution is significantly higher than this peak in the distribution. So you might conclude that, well, for some reason my quantum dot spends more time in the up state than the down state. But that's not actually what's happening. There's noise in the system. And that brings me on to the second problem, second challenge facing quantum dots. It's noise. So quantum dots are subject to noise from their local environment. There's charge traps inside and around the quantum dot area, perhaps on the edges of edge structures around the quantum dot. There's also a large nuclear spin, about 10 to the 5 nuclei, and both of these act to change the local and electric magnetic fields around your quantum dot. So one way this can manifest itself is in spectral wander. So, for example, my quantum dot, the electric fields and the magnetic fields of my quantum dot could be configured in such a way that they shift the spectral resonance of my quantum dot out of the way. So if you imagine this dashed red line is my input vertically polarized photons, there's going to be certain times where my quantum dot's moved out of the way because the quantum dot environment's in the wrong state, if you like. But also there's going to be instances where my quantum dot environment's in the correct state, and at those times my input photons will be exactly on resonance with my quantum dot. So you might think at first glance, this sounds horrible. I don't know what energy my quantum dot has at any given time. That's awful. But it turns out the timescales for this wander tend to be typically quite slow. So in our system, we've measured two timescales, one at 250 microseconds, one at 1.5 milliseconds. And the point is, that's incredibly long compared to the time it takes to interact with our quantum dot. So that's defined on the sort of nanosecond timescale of our exciton lifetime. So what that means is one kind of route to get through this spectral wander kind of noise is to brute force. So the tactic is these systems are so bright that you can collect so many photons in a very short time window that the quantum dot environment hasn't had time to shift to a new configuration. And that's what we did basically in that switching data I showed you. And it's actually how people get the best reported indistinguishabilities from the single photon sources in the pulse regime. They're really interfering two photons that have been produced only a few nanoseconds apart in time, so the quantum dot environment hasn't had time to mess up. But also that's a bit unsatisfying, and I think really the main problem we're going to have with noise in quantum dots, as Mette highlighted, is with the nuclear spins. Particularly when we come to prepare superpositions of electron spin states, they're particularly sensitive to dephasing by the local nuclear spin bands. So what we really need to do is implement schemes to calm down and freeze out the fluctuations in that nuclear spin environment. So this experiment was done a long time ago now, actually, and was in ensembles of quantum dots. And what they did is implement specific pulse sequence, optical pulse sequence on their electron, and as they do that, it effectively feeds back information onto the nuclear spin band, and they could end up freezing out the local nuclear spin fluctuations. And they saw in that instance they really calmed down the nuclear spin bath and really improved the electron spin dynamics. And also we just saw in Mette's talk, this has now been moved on to single quantum dots, where this time they're using coherent population trapping, but it's the same idea. You're feeding back information from the electron spin onto the nuclear spin bath and preparing it in a favourable state. And it's gone up in an order of magnitude in terms of the coherence of the electron spin. So these results are really, really encouraging for single quantum dot work. And we're working on similar things in Bristol. Jana, who's sat at the back, and Dara have been working on some theory. We should be doing an experiment soon. So maybe BQIT 2019 will have some complementary results to show you on that. But that brings me to my summary slide, really. Quantum dots, as we've seen from this talk and all the previous ones, are really on the cusp of being a viable quantum technology. But the photon injection and collection efficiency really needs to be improved in order for things to scale nicely when we really want to start doing quantum information things. And a biggie is the nuclear spin environment. If we want to do anything beyond single photon sources with these devices, then we really need to understand that nuclear spin environment and bring it under control. That's the end. That's everything I've got to say.
Thank you, Andrew. Do we have any questions for Andrew? Alex?
Thanks, Andrew. One question is, many people have tried to extract photons from high-index media by using something like an inverse taper, where the mode can then expand into air, and then you remove this Fresnel reflections at the interface. Have people tried this with these pillars, or is it just really hard to get this fabrication to work?
We're trying it, yeah. So. To answer that question very briefly, but yeah, fiber tapers are another thing that we're looking at to get light in and out of these structures.
Any more questions? I think people are running out of energy at the end of the day. If that's the case, then let's thank Andrew again. So just two more.